Good morning. My name is Varsa from BSc First Year Chemistry Honors. Today our chapter name is Structure and Bonding. Introduction to Organic Chemistry. The term organic compounds was originally applied to compounds such as sugar, alcohol, oils, and fats, which are derived from vegetable or animal sources. That is, from living organisms. This was done in order to differentiate such compounds from inorganic substances such as common salt, sulfur, and metals, which are obtained from mineral resources. The study of organic compounds gradually began to develop as a separate branch of chemistry, which came to know as organic chemistry. The chemistry of inorganic compounds was therefore distinguished by calling that inorganic chemistry. Vital force theory. In the early days of the growth of organic chemistry, it was considered impossible to prepare organic compounds in the laboratory. Berzelius in 1815 suggested that organic compounds could be produced only under the influence of some mysterious forces exciting in living organisms. This force was called vital force, from the Latin word vita equal to life, and the theory of Berzelius come to know as a vital force theory. However, in 1828, Wohler synthesized urea, an organic compounds present in the urine of animals, from ammonium cyanide, an inorganic compound obtained from ammonium sulfate and potassium cyanide. When ammonium cyanide reacts, urea is formed. This synthesis of organic compounds in the laboratory shook the faith in the vital force theory. In 1845, Colby synthesized acetic acid from inorganic sources, and the laboratory synthesis of many other organic compounds soon followed. Consequently, the idea of vital forces was completely discarded by in 1850, and it was firmly established that formation of organic compounds does not depend upon any special force. Thereafter, the number of synthetic organic compounds began to rise at an ever growing rate. Modern definition of organic compounds. With the rejection of vital force theory, the major difference between organic and inorganic compounds disappear and the terms lost their original significance. But organic chemistry continued to be treated as a separate branch of chemistry, although it was given a new definition. Organic chemistry is now defined as the chemistry of the compounds which contain carbon as an essential constituent. A few compounds of carbon, such as carbon monoxide, carbon dioxide, and carbonates, are, however, studied in inorganic chemistry, which deals with the study of all other elements and their compounds. The simplest organic compounds are hydrocarbons, which are made up of carbon and hydrogen. All the organic compounds can be considered to have been derived from hydrocarbons by the replacement of one or more hydrogen atoms by other atoms or groups. Therefore, organic chemistry can also be defined as the chemistry of hydrocarbons and their derivatives. Theoretical aspects of organic chemistry. There has been a strong growth of theoretical understanding in the field of organic chemistry in the last few decades. This has been very helpful in interpreting the details such as mechanism, rate of occurrence, and the effect of temperature, concentration, etc. of the large variety of chemical reactions encountered in organic chemistry. In order to appreciate the theoretical aspects of the subject, the student must have a clear understanding of certain fundamental concepts. We are introducing a few relatively simple concepts in this chapter. Nature of bonding in organic compounds. The carbon atom, atomic number 6, which is the common feature of all organic compounds, has the electronic configuration 1s2, 2s2, 2px1, 2py1, and 2pz0. Thus, it has got 4 electrons in the valence shell. In order to acquire a stable noble gas configuration in its compounds, carbon should either lose or gain 4 electrons or alternately share 4 electrons. But the loss or gain of 4 electrons leading to the formation of C plus 4 or C minus 4 ions would require the supply of very large amount of energy which is not available during the ordinary chemical processes. This implies that carbon cannot form ionic bonds in its compound and must form only covalent bonds. In other words, covalent bond is the bond of main importance in organic chemistry. According to orbital concept, a covalent bond is formed when a half-filled valence orbital of an atom overlaps a half-filled valence orbital having an oppositely spinning electron of another atom. Now a carbon atom has got only two half-filled valence orbitals and therefore it may be expected to form only two covalent bonds. But in actual practice, carbon is known to have a covalency of 4 in its compounds. To explain the tetracovalency of carbon, it has been now postulated that at the time of bond formation, the two electrons in the 2s orbital of carbon are unpaired and one of them is promoted to the empty 2p orbital. This gives rise to the electronic configuration 1s2, 2s1, 2px1, 2py1, 2pz1 as shown below. In its new state called excited state, the carbon atom has 4 half-filled valence orbitals which would be available for the formation of covalent bonds. Thus, carbon atom exhibits a covalency of 4. It may be noted that formation of 4 bonds by carbon would result in greater lowering of energy and formation of more stable molecules than if carbon were to form only 2 bonds. This extra lowering of energy more than compensates the energy needed to promote an electron from 2s to 2p orbital. This means that even though the promotion of electron is by itself not favored energetically since it takes place with adsorption of energy, it ultimately leads to greater lowering of energy by enabling carbon to form 4 bonds in place of only 2 as illustrated ahead. Thus, there is net release of 836 kg per mole in the formation of CH2, while there is net release of 1672 minus 400 equal to 1272 kg per mole in the formation of CH4. Bond energy. The process of bond formation is accompanied by release of energy, and the bonded state represents a state of lower energy than the individual atoms. It therefore follows that an equivalent amount of energy will have to be supplied to break the bond. The amount of energy required to break a bond and separate the bonded atoms in the gaseous state is known as bond dissociation energy or simply bond energy. This is generally expressed in kg per mole. Thus, hydrogen molecule has a bond dissociation energy of 433 kg per mole. It may be mentioned that bond energy is also equal to the amount of energy released when 1 mole of hydrogen atom combines with 1 mole of hydrogen atom to form 1 mole of hydrogen molecule containing 1 molecule of hydrogen bonds as. It is apparent that bond energy is a measure of the strength of a bond. Greater is the bond energy, stronger is the bond. Factor on which bond energy depends: size of bonded atoms. Bond energy is inversely proportional to the size of bonded atoms. The greater the size of the bonded atom, smaller is the bond energy. This is because in bigger atoms, the overlapping of atoms orbital is less effective. Bond length. The smaller the bond length, higher is the bond energy. Smaller bond length means greater the strong overlap of atomic orbitals, which results in greater bond energy. Third is nature of rest of molecule. The energy required to break a particular bond between two atoms has a specific value only for that bond and is generally termed as bond dissociation energy. But when a certain bond may be present in a molecule of different substances, the actual value of bond dissociation energy of that bond will vary from one compound to other. For instance, OH bond may be present in water as well as in methyl alcohol. The bond dissociation energy of OH bond in water is different than its energy in methyl alcohol. In a polyatomic molecule, even the energy required to break a particular kind of bonds may have different values. For example, the four CH bonds in CH4 are equivalent, but the energy required to break the first bond is not the same as the energy required to break the second bond, and so on. This difference in the bond energies of the even the same kind of bonds is due to the fact that the energy of a bond depends upon the nature of the rest of the molecule as well. Therefore, when giving the general values of bond dissociation energy of such bonds, only the average value are stated. The average value are generally referred to as a bond energy rather than bond dissociation energy. The bond energies of some bonds are given in table 1.1. The values of bond energies given in this above table for HH, HCl, HBr and HI are their actual bond dissociation energies, while the values given for the bonds are the average bond energies. Localized and delocalized chemical bonds. Localized chemical bond. When a covalent bond is formed by the overlap of two atomic orbitals, the orbitals that result are property of the molecule, not of the individual atoms. That is why the resultant orbitals are known as molecular orbitals. The electrons in these orbitals are shared between the atoms involved in bond formation. For example, let us consider the formation of hydrogen molecule from two hydrogen atoms, each having one s electron with antiparallel spin relative to other when the 1s orbital of two atoms overlap with two 1s electrons become paired and begin to occupy the same molecular orbital. This probability of finding these electrons is greatest in the region between the two nuclei. It is due to this concentration of negatively charged electrons between the two positively charged nuclei that the two nuclei are bound together. It may be pointed out that even though both the electrons are negatively charged, they tend to concentrate in the internuclear region due to their antiparallel spins. The net result is that electron density of the electrons involved in the bond formation is greatest in the region between the two nuclei. Therefore, the two paired electrons are said to occupy a localized molecular orbital, and the bond formed is known as localized bond. A localized bond may therefore be defined as the bond whose electrons are greatly concentrated in the region between the two nuclei only. A sigma bond between any two atoms, a pi bond between two atoms in a molecule having only one double bond, or the pi bonds in a molecule having isolated double bonds are localized bond. In figure 1.2, all bonds shown above the including CH bonds are localized bond. Delocalized chemical bonds. To understand the concept of delocalized chemical bonds, let us consider the case of molecule containing double bonds and single bonds in alternate position. Double bonds which alternate the single bonds are said to be conjugated. For instance, 1,3-butadiene is conjugated diene while 1,4-pentadiene is non-conjugated diene having isolated double bonds. Structure of 1,3-butadiene and structure of 1,3-pentadiene. Let us now discuss the molecule of 1,3-butadiene is typical case of the formation of delocalized chemical bonds. Each of the four carbon atoms of 1,3-butadiene is in sp2 hybrid state having 3 sp2 hybrid orbitals and one hybridized p orbital. The 3 sp2 orbitals of each carbon are used in the formation of sigma bonds with adjacent carbon and hydrogen atoms, and all these bonds are localized bonds. The anhybridized p orbital of the carbon atoms are used in the formation of pi bonds. In figure 1.3a shows anhybridized p orbital of the carbon atoms of 1,3-butadiene before the formation of pi bonds. Overlap p orbital of 1s with that of 2c, and of the p orbital of 3c with 4c are shown in figure 1.3b. However, if the molecule is planar, then the p orbital of 2c can also overlap there is overlapping of p orbital of 1c with 2c, 2c with 3c and 3c with 4c as shown in figure 1.3d. Therefore, all the 4p orbitals can be treated as forming pi molecule orbital which covers all the 4 carbon atoms in figure 1.3e. In this condition, we do not have pairs of electron mainly confined. A molecular orbital which is separate over the nuclei of more than 2 atoms is known as delocalized molecular orbital, and the electron present in it termed delocalized electrons. The bonds thus formed are called delocalized bonds. A delocalized bond may be defined as the bond whose electrons are spread over the nuclei of more than 2 atoms, as in case of normal or localized pi molecular orbital. Delocalized molecular orbital are also consist of 2 electron clouds, one lying above the plane of atom and other lying below it in figure 1.3e. Figure 1.3a represents the p orbitals of the 4 carbon of 1,3-butadiene before the formation of pi bonds. Figure b represents the overlap of p orbital of 1c with 2c with 3c with 4c. Figure C represents the overlap of p orbitals of 2c and 3c. Figure D represents the overlap of p orbitals of 1c with 2c, 2c with 3c and 3c with 4c. Figure E represents the delocalized pi molecular orbital of 1,3-butadiene. Effect of delocalization of bonds. The delocalization of bond has the following effects on the system involved. First is effect on the bond length. The formation of delocalized bonds causes a bond length to change from the normal value of single, double and triple bonds. For example, the bond lengths between any two adjacent carbon atoms in 1,3-butadiene is 149 picometer. Neither correspond to carbon-carbon bond length 154 picometer nor carbon-carbon double bond length 134 picometer. Effect on movement of electrons. In delocalized bonds, the electrons have greater freedom of movement than in localized bonds. Effect on stability. Delocalization of bonds leads to a decrease in the energy of the system. In other words, delocalization of bonds makes the molecule worlds more stable. This energy of stabilization is known as delocalization energy. For example, delocalization energy of 1,3-butadiene is nearly 16 kg per mole. Kinds of molecule which contain delocalized bonds. Delocalization of bonds is exhibited by 3 main kinds of structures. First is double or triple in conjugation. Apart from 1,3-butadiene discussed above, benzene is another important example of molecules containing multiple bonds in conjugation which exhibit delocalization as discussed below. All the carbon atoms of benzene ring are in state of sp2 hybridization. The 3 hybridized orbitals of each carbon are involved in the formation of 3 sigma bonds, 2 with adjacent carbon atoms and 1 with hydrogen. As far as the unhybridized p orbital of each carbon atom is concerned, it can overlap to a small but equal extent of unhybridized p orbital of both the adjacent carbon atoms. Thus, the odd electron in the unhybridized orbital of each of 6 carbon atoms can form pi electron cloud involving more than 2 atoms. In other words, the pi electrons are spread over or extensively delocalized, and this results in the formation of a molecular orbital embracing all the 6 carbon atoms. The net result of this delocalization is that there are 2 continuous ring-like electron clouds, one lying above the and the other below the plane of the atom as shown in figure 1.4. Delocalized bonds in benzene. Second is double or triple bonds in conjugation with a p orbital on an adjacent atom. The presence of a p orbital which may have 2, 1 or no electrons on an atom adjacent to a multiple bonds also leads to the formation of delocalized bond. For example, in vinyl chloride, the p orbital of chlorine having a lone pair of electrons overlaps with carbon-carbon double bond to cause delocalization as shown in the figure on right hand side. La like carbanion affords another example of structure exhibiting delocalization in which p orbital on adjacent atom to multiple bond contains two electrons. Structure in which the p orbital on adjacent atom contains only one electron are found in free radicals, while the structure in which the p orbital does not contain any electron are come across in carbocations. Hyperconjugation. This type of delocalization involves CH sigma bonds adjacent multiple bonds and is discussed later in section 1.8. Van der Waals interactions. Intermolecular forces. Intermolecular forces are the attractive forces which operate between molecules of the same or different substances. These forces can be divided into different types depending upon the nature of the molecules. For instance, in covalent bonds containing polar bonds, partial negative and positive charges are produced on atoms by unequal sharing of electron pairs. As a result, majority of these molecules possess a dipole moment. In such cases, the negative end of the molecule will naturally attract the positive end of another molecule to give rise to intermolecular forces known as dipole-dipole attraction. However, non-polar molecules also have weak intermolecular forces as discussed below. Non-polar molecule substances such as oxygen, nitrogen, chlorine, and methane exist in the gaseous state in the form of individual covalent bonds molecules, but when such substances as well as the noble gases undergo condensation at low temperature to liquid and solid states, which is accompanied by decrease of energy. This led to the suggestion by van der Waals as a Dutch physicist that there must be some weak intermolecular interaction between such molecules which become relatively strong in the liquid or solid states. Subsequently, these forces come to be termed as van der Waals forces or interaction. They may be defined as very weak forces of attraction between non-polar molecules which arise from the movement of electron in atom and molecules. That these forces are quite weak is evident from the fact that non-polar molecular substances and noble gases have very low boiling points. This can be possible only if the intermolecular forces are weak and are overcome by supplying very small amount of energy. Origin of van der Waals forces. To understand the origin of these forces, let us consider two helium atoms very close together. Ordinarily, in each atom, the charge of the electron is symmetrically distributed around its nucleus. However, since the electrons move about freely, we can imagine that at a particular instant of time, the electron distribution in atom has become somewhat unsymmetrical with a slight increase in electron density on one side. Therefore, for a very small fraction of a second, this atom has one end very slightly negative relative to the other end. This temporary separation of positive and negative charges produces an instantaneous or temporary dipole. Figure 1.5 represents the origin of temporary dipole. Figure 1.6 represents the dipole on one atom can induce a dipole on neighboring atom. The temporary dipole in turn influences the electron distribution of another atom present in its neighborhood because the negative end of atom 1 repels the electron of atom 2. As a result, there is an instantaneous induced dipole in the neighboring atom. Although this picture persists for an extremely short time and the momentary and induced dipoles are constantly changing, the net result is a force of attraction between the neighboring atoms. Similarly, in case of non-polar molecules such as methane and carbon tetrachloride, the average distribution of charge about the molecule is symmetrical and there is no net dipole moment. However, the instantaneous increase or decrease in the electron density in a particular region creates very short-lived temporary dipoles in portion of the molecule. These dipoles induce oppositely oriented dipole in neighboring molecules so as to result in a net attraction between different molecules. The forces of attraction between non-polar molecules due to temporary dipole-induced dipole interactions constitute van der Waals interaction. They are also known as London forces or depression forces. Factors influencing van der Waals forces. As already remarked, the van der Waals forces are very weak and effective over extremely small distances. The actual magnitude of these forces depends mainly upon the following factors. First is number of electrons in the molecule. The magnitude of van der Waals forces depends upon the number of electrons in atom or a molecule. With the increase in the number of electrons, there are more chances for the electron distribution to become unsymmetrical. As a result, the magnitude of van der Waals forces increases. Second is size of the molecule. As the molecular size increases, the surface area becomes larger. Consequently, the chances of unsymmetrical electron distribution increase and the van der Waals forces become stronger. Since the increase in molecular size generally runs parallel to this increase in molecular weight for the same type of substances, therefore the van der Waals forces also become relatively stronger with the increase in molecular weight. That is why the boiling points of a series of similar compounds generally increase as the molecular weight increases. For instance, the boiling points of alkanes increase gradually from methane to ethane to propane and so on. Third is molecular shape. The magnitude of van der Waals forces also depend upon the shape of the molecules. To illustrate the statement, let us consider the case of N-pentane and neopentane. N-pentane is a straight chain molecule having a large surface area, while neopentane is a compact molecule having much lesser surface area. There are structure of N-pentane and neopentane. Due to greater surface area of N-pentane, there are more chances for the molecules of this compound to interact with each other. As a result, the magnitude of van der Waals forces is large. On the other hand, the chances of a molecular interaction are much less in neopentane due to the compact shape of the molecule. Hence, the magnitude of van der Waals forces is very small. That is why neopentane has much lesser boiling point, 283 Kelvin, than N-pentane 3. Fourth is temperature and pressure. It may also be noted that for the same substance, the van der Waals forces are relatively stronger at low temperature and high pressure. At low temperature, the random movement of the molecule decreases, which provides greater opportunity for molecular interaction. Naturally, therefore, the van der Waals forces are relatively stronger. At high pressure, the molecule get closer so that there is stronger interaction between neighboring molecule and therefore the van der Waals forces are also stronger. Types of van der Waals interaction. It may be pointed out that apart from intermolecular forces between non-polar molecules due to temporary dipole-induced dipole interaction, the term van der Waals interaction also includes the following two types of attractive forces. First is dipole-dipole attraction. As already stated, these are forces of attraction which operate between molecules which are permanently polar in nature, such as HCl, NH3, SO2, and acetone. Second is dipole-induced dipole attraction. These forces operate between molecules, one of which is polar and the other is non-polar. Under the influence of polar molecule, a temporary dipole is induced in the non-polar molecule. This gives rise to dipole-induced dipole kind of attraction. For example, there is a weak interaction of this type between water molecules and xenon gas due to which xenon is sparingly soluble in water. Van der Waals repulsions. The magnitude of van der Waals forces of attraction increases as the distance between the non-bonded atoms or molecules decreases. The attractions becomes maximum when the distance between the non-bonding atoms or molecules reaches a certain minimum value. This minimum distance at which the forces of attraction is maximum is equal to the sum of van der Waals radii of non-bonded atoms or molecules. If non-bonded atoms come so close to each other that the distance between them is lesser than the sum of their van der Waals radii, the attractive interaction turns into repulsive interaction. For example, in the Bott conformation of cyclohexane, there is a repulsive interaction between two flagpole hydrogens. This is because the distance between them is 183 picometer, which is less than sum of their van der Waals radii. Resonance. It has already been studied in earlier classes that the concept of resonance or Mesomerism was put forward to explain the structure of compounds such as benzene. It has been suggested that if a molecule can be assigned two or more conventional valence bond structure, each of which can explain most of but not all the observed properties of the compound. The actual structure lies somewhere in between the various possible conventional structure. The various possible structure are called contributing or canonical structure, and the actual structure is called resonance hybrid. The resonance hybrid is indicated by putting a double-headed arrow between the contributing structure. The concept of hybridization of two or more conventional valence bond structure to arrive at an internally new and individual structure, which however cannot be depicted on paper in terms of conventional formula, is termed as resonance. One of the most well-known example of this application of resonance is afforded by benzene. Since benzene could not be assigned any satisfactory valence bond structure which could explain all the properties, it was proposed that benzene is a resonance hybrid of structures 1 and 2. This implies that the structure of benzene is presented neither by one nor by second, but lies somewhere in between the two. It is evident that in the resonance hybrid, the bonds which link the carbon atoms neither correspond to single nor double bonds. On the other hand, all the bonds are equivalent and are intermediate between single and double bonds. This has been confirmed by X-ray diffraction studies which show that all the carbon-carbon bonds in benzene are of exactly the same length, which is in between that of carbon-carbon single bond, and the carbon-carbon double bond length is 1.34 angstrom. The resonance hybrid structure of benzene has 151 kg per mole of energy, less than either of the contributing structures. This represents the resonance energy of the molecule. It is the energy which is responsible for the unusual stability and remarkable behavior of benzene. Other examples of resonance. First is carbon dioxide. Carbon dioxide is considered to be resonance hybrid of three contributing structure as shown below. The observed bond length of carbon-oxygen bond is carbon dioxide is lesser than that of carbon-oxygen double bond, which can be justified in terms of its resonance hybrid structure. Second is carboxylic acids. The acidic character of carboxylic acid is explained by treating the carboxylic acid as the resonance hybrids of the following contributing structures. Third is 1,3-butadiene. 1,3-butadiene and other conjugated dienes also exist as resonance hybrids. For example, 1,3-butadiene is a resonance hybrid of three contributing structures. Condition for resonance. According to the general theory of resonance, the various conventional structure formula contributing to the structure of resonance hybrid must satisfy the following condition. First is the various contributing structures should differ from each other only in the position of electrons, where the relative arrangement of atoms and their state of hybridization must be the same. Second is the atoms involved must lie in the same or nearly the same plane. Third is the number of paired and unpaired electron in each contributing structure must be the same. For example, when CH2 single bond CH double bond CH single bond CH2 is not valid contributing structure for butadiene since it has more unpaired electron than other contributing structures. Fourth is all the contributing structure must show the correct number of valence electron for the elements of second period. No contributing structure should have more than 8 electrons in the valence shell of the element. For example, when CH2 single bond CH have double bond with NH3 cannot be considered as contributing structure since in it nitrogen has 10 electron in the valence shell, which is not possible. All the contributing structures should have the same or nearly the same amount of energy and stability. When the contributing structures differ in energy, content, or relative stabilities, their more stable structure makes greater contribution towards the resonance hybrid. Seventh is in determining the relative stability of contributing structures, the following points may be noted. First is the larger the number of covalent bonds in a structure, the greater is the stability. For example, first structure is more stable than the second structure. Second is the structures involving separation of positive and negative charges are less stable than those which do not involve any separation of charges. First structure is more stable than that of second structure. Third is when atoms of different electronegativities are involved, the structure having negative charge on more electronegative atom and positive charge on less electronegative atom are relatively more stable than the other way round. For example, first structure is more stable, second structure relatively more stable than third structure, and third structure is less stable. Fourth is the structures having like charges or adjacent atoms are highly unstable. First structure is more stable than that of second structure is highly unstable. The more the number of contributing structures, the more stable is the resonance hybrid. Properties of resonance hybrid. First is stability. A resonance hybrid is always more stable than any of the contributing structures. The extent of greater stability of the resonance hybrid depends upon the number of contributing structures and their relative stabilities. Second is resonance energy. It is measure of stabilization due to resonance and may be defined as the difference in energy between the energy of the resonance hybrid and its most stable contributing structure. Greater the resonance energy, greater is the stability of resonance hybrid. For example, the resonance energy of benzene is about 151 kg per mole. The value of resonance energy can be determined from the data involving heat of hydrogenation and heat of combustion etc. Bond lengths. In a resonance hybrid, the bond lengths are different from those in the contributing structure. For instance, the carbon-oxygen bond length in carbon dioxide is 1.15 angstrom as against the value of 1.22 angstrom for a carbon-oxygen double bond length. It may be seen that the concept of resonance hybridization is essentially equivalent to the delocalization of electrons. It is the delocalization of electrons which leads to the formation of stronger bonds and more stable molecules. Therefore, the term delocalization energy is often used in place of resonance energy. Resonance effect. It is a process of permanent displacement of electrons in a molecule brought about by resonance or mesomerism. Unlike inductive effect, resonance or mesomerism effect is transmitted through pi electrons and operates an unsaturated system, particularly those containing a suitable atom or a group of conjugation. With unsaturated system, for this reaction it is also termed as conjugative effect. What happens is the resonance effect causes delocalization of electrons and gives rise to additional contributing structure due to withdrawal or release of electrons by the given group. For example, in the molecule which contains C double bond O group in conjugation with C double bond C. Electron withdrawal by C double bond O group causes delocalization of electron and give rise to an additional structure as shown below. Types of groups involved in resonance and their resonance effect. First is groups having electron withdrawing resonance effect -R or -M effect. Groups such as NO2, C double bond O, C triple bond N, SO3H and C double bond OR withdraw electrons from an unsaturated linkage through resonance and are said to have -M or -R effect. For example, the given reaction. Second is group having electron releasing resonance effect plus R or plus M effect. Groups such as OH, OR, NH2, NHR, NR2 which can release electrons through resonance are said to have plus M or plus R effect. These groups have one or more lone pair of electrons which they furnish for conjugation with unsaturated system. It is important to remember that unlike inductive effect, resonance effect suffers practically no decrease in intensity with the increase in distance along the chain of atoms. Applications of resonance effect. Resonance effect is very useful in explaining the stability, assay of formation and reactivity of many chemical species, as illustrated below. First is low reactivity of vinyl halides and aryl halides. As compared to alkyl halides, vinyl halides exhibit very low reactivity in nucleophilic substitution reactions. This is because the halogen atom in vinyl halide causes delocalization of electrons due to plus R effect and gives rise to an additional contributing structure as shown below. Due to resonance stabilization, the halogen atom gets more firmly attached to the carbon and is not displaced readily. Similarly, low reactivity of aryl halides towards nucleophilic substitution can be explained in terms of resonance stabilization. Second is acidity of carboxylic acid. The acidic nature of carboxylic acid is due to their ionization in aqueous solution to form carboxylate ion and hydronium ion. The carboxylate ion is stabilized by resonance due to minus R effect of C double bond O group. This makes the formation of the ion easily possible and is mainly responsible for the acidity of carboxylic acids. Even in undissociated carboxylic acids, resonance is possible, but this involves separation of charge. As such, it is much less effective than in carboxylate ion, where the resonance forms are identical. Therefore, carboxylate ion is stabilized by resonance due to a greater extent than carboxylic acid, which explains the tendency of carboxylic acid to undergo ionization. We will encounter many more examples of resonance effect in explaining the assay of formation, relative stabilities and relative reactivities of many species during the course of our study. Hyperconjugation or no bond resonance. The concept of hyperconjugation was put forth by Baker and Nathan in 1935 as a result of certain observations concerning the inductive effect of alkyl group attached to an unsaturated system such as double bond or benzene ring. An alkyl group has electron releasing inductive effect plus I effect, and the order of plus I effect of different alkyl groups is CH3 whole cubic C greater than CH3 twice CH, CH3 CH2 more than CH3. But when an alkyl group is attached to an unsaturated system such as double bond or benzene ring, the above order of inductive effect gets reversed. To account for these observations, Baker and Nathan put forward the concept of hyperconjugation, also referred to Baker-Nathan effect. Hyperconjugation is another kind of resonance or delocalization of electrons which takes place through overlap between a p orbital or a pi orbital and a sigma orbital of an adjacent CH bond. For instance, let us consider the delocalization of electrons in alkene, where represents an alkyl group attached to C double bond C. Delocalization here may be shown as in this figure. It is clear that the delocalization involves overlapping between a sigma orbital of the CH bond of alkyl group and the pi orbital of C double bond C bond. As a result of overlapping, each of the delocalized electrons is involved in binding together not merely two atoms, but it helps in binding together all the four atoms to some extent. In terms of resonance, the above situation may be taken to mean that the given alkene is a resonance hybrid of canonical forms as first and second. Whether we look at hyperconjugation in terms of orbital overlap or resonance, what happens is that there is an interaction between sigma electron of CH bond and pi electron of adjoining C double bond C bond. In actual practice, this means that CH bond of alkyl group is slightly less than a single bond. C2-C3 bond has some double bond character while C1-C2 bond has some single bond character. These conclusions are supported by the experimental determination of various bond lengths in propene and other alkenes. Explanation of observed order of inductive effect of alkyl group when attached to benzene ring or any other unsaturated system such as CH double bond CH2. It has been stated that above that the usual electron releasing inductive effect of alkyl groups follows the order, but when attached to benzene ring or many other unsaturated system, or the order of inductive effect becomes This may be understood as follows. When a methyl group is attached to an unsaturated system, as in propane, the various hyperconjugative structure possible are. On the other hand, when an ethyl group is attached to an unsaturated system, as in butane, the number of hyperconjugative structure possible is lesser as shown below. This is because the number of hyperconjugative structure possible depends upon the number of hydrogen atoms, which is directly linked to unsaturated since only these hydrogens participate in hyperconjugation. Now ethyl group has only two alpha hydrogens, whereas methyl group has three such as hydrogens. Similarly, the number of hyperconjugative structures possible for CH3 twice CH will be still lesser, and no such structure will be possible for CH3 cube C. As the number of possible hyperconjugative structures goes on decreasing, the electron releasing tendency of alkyl group goes on decreasing. Application of hyperconjugation. The concept of hyperconjugation is widely used in the study of organic chemistry. For example, first, it helps to explain the relative stabilities of alkenes. Second, it is used to explain the relative stabilities of carbocation and free radicals. Inductive effect. The concept of inductive effect concerns the shift of electrical charge within a molecule arising out of the presence of a polar covalent bond in the molecule. To illustrate this, let us consider a molecule having a chain of carbon atoms with a chlorine atom linked to and carbon atoms such as 4C3C2C 1CCl. Due to greater electronegativity of chlorine, the electron pair of the bond between 1C and Cl is displaced towards chlorine atom. As a result, polarization of the bond takes place. Chlorine acquires a small negative charge while 1C becomes slightly positively charged as shown below. Now the positively charged 1C exerts an attractive influence upon the electron pair shared between 1C and 2C. Due to the resultant electron displacement towards 1C, the positive charge on 1C is partially neutralized while a small positive charge develops on 2C. But the charge on 2C is smaller than that of 1C. The positively charged 2C in turn attracts the electron pair of the bond between itself and 3C, thereby making 3C also very slightly positively charged. This process of electron shift along the chain of atoms due to the presence of a polar covalent bond in a molecule is known as inductive effect. It is represented by an arrow shown below. Inductive effect is sometimes also called transmission effect. Because it is transmitted through the bonds constituting the chain of atoms, it should be noted that the effect along the chain of atoms is not the same throughout. It decreases sharply as we move away from the initial polar bond and is negligible from fourth atom upward. It must also be understood that inductive effect does not involve any actual transfer of electrons from one atom to another. It merely helps in displacing them permanently. Types of inductive effect. Inductive effect is a relative effect and may involve attraction of electrons towards a group or repulsion of electrons away from it. For comparing the relative inductive effect of various groups, hydrogen is commonly taken as the standard and the accordingly groups are divided into the categories. First is electron withdrawing inductive effect. Atoms or groups which have greater electron attracting capacity than hydrogen are said to have -I effect. The decreasing order of -I effect of some common groups as follow. It may be noted that compared to hydrogen, most groups are electron withdrawing. Second is electron releasing inductive effect. Atoms or groups which have lesser electron attracting capacity than hydrogen are said to have +I effect. The most important electron releasing groups are alkyl groups. At the same time, many groups having formal negative charge and atoms of low electronegativity such as silicon, magnesium and lithium are electron releasing. The decreasing order of some groups having +I effect is as follows. It may be noted that in case of alkyl groups, the more highly substituted the alkyl group, the greater is its +I effect. Application of inductive effect. Inductive effect plays a very important role in organic chemistry as illustrated below. First is comparison of relative acidic strength of organic acids. In aqueous solution, a carboxylic acid exists in equilibrium with the carboxylate anion and a hydronium ion that is as shown in this reaction. The strength of the acid is generally expressed in terms of equilibrium constant Ka, which is given by the expression. Since A is directly proportional to the concentration of H3O positive ions, it would have a low value in case of weak acids and high value for strong acids. The position of the equilibrium in the reaction between a carboxylic acid and water to furnish carboxylate anion and the hydronium ion depends upon the stability of the products relative to the stability of the reactants. Any factor which stabilizes the carboxylate anion more than the parent acid should increase the acidity, and the factor which destabilizes the anion should decrease the acidity. A group having electron withdrawing inductive effect on the carboxylate anion attracts electron towards itself and thus disperses the negative charge of the anion. As a result, it stabilizes the carboxylate anion and thus increases the acidity of the parent acid. A group having electron releasing inductive effect on the carboxylate anion intensifies the negative charge of the anion and thereby destabilizes the anion. Consequently, it decreases the acidity of the parent acid. In short, it may be stated that the electron withdrawing groups increases the acidity of the electron releasing groups, decreases the acidity of carboxylic acid. Let us, for instance, compare the acidities of acetic acid and chloroacetic acid. It is found that chloroacetic acid is about 80 times stronger than acetic acid. This is due to the fact that an acetic acid, the electron releasing inductive effect of methyl group destabilizes the carboxylate anion. On the other hand, the chlorine present in chloroacetic acid exerts an electron withdrawing inductive effect and thus stabilizes the carboxylate anion by dispersing its negative charge. The reactions showing CH3 group has electron releasing effect and tends to intensity the negative charge on oxygen. Reaction 2 shows that chlorine has electron withdrawing effect and tends to disperse the negative charge on oxygen. Similarly, it can explain why acetic acid is weaker than even formic acid. Acetic acid contains the CH3 groups having electron releasing inductive effect attached to the carboxylic group, which destabilizes the carboxylate anion by intensification of charge. On the other hand, formic acid has only a hydrogen which has no destabilizing effect on the carboxylate anion. Second is comparison of relative basicities of amines. Like ammonia, all amines are basic in nature. A convenient way of expressing the basic strength of amines is in terms of equilibrium constant Kb, which is derived from the following equilibrium. The greater is the value of Kb, the greater is the basicity of amines. The basicity of amines depends upon the availability of electron pair on nitrogen atom and the stability of the substituted ammonium ion formed. Any factor that increases the availability of electron pair on nitrogen or increases the stability of ammonium ion relative to the parent amine will increase the basicity of amine. On the other hand, any factor that has the opposite effect will decrease the basicity. It has been found that aliphatic amines have greater basicity than ammonia. This can be explained in terms of electron releasing inductive effect of alkyl group. Aliphatic amines contain one or more alkyl groups in place of hydrogen atoms of ammonia. Now an alkyl group being electron releasing increases the electron density on nitrogen and thus makes the electron pair on nitrogen more available for sharing. At the time the electron releasing inductive effect of alkyl groups decreases the positive charge of the substituted ammonium ion formed by the amine and thus increases its stability. In fast structure, R helps to increase the electron density around nitrogen and makes the electron pair more available. In second structure, R disperses the positive charge of the ion and thus increases its stability. Third is comparison of basic strength of ethylamine and acetamide. Ethylamide is much more base than acetamide. This is because the plus I effect of the ethyl group of ethylamine increases the electron density on nitrogen, which gets easily protonated. In structure fast plus I effect of C2H5 high electron density on nitrogen. In structure 2 reduced electron density on nitrogen due to resonance. On the other hand, the electron pair on nitrogen of acid might get delocalized due to the resonance. As a result, electron density on nitrogen decreases and its basic character gets suppressed. Fourth, comparison of relative stabilities of species such as carbocation and carbon anions. Fifth is cause of reactivity of many compounds. Inductive effect helps us in understanding the cause of reactivity of many compounds as discussed at appropriate places in the text. Comparison of resonance and inductive effect. In resonance effect operated in an unsaturated system, particularly in conjugated system through the pi electrons. But in inductive effect, it operates even in saturated system. Presence of unsaturation is not a necessary condition. Second is it involves the displacement of non-bonding and pi electrons. Second, it involves displacement of sigma electrons. Third is during the resonance electron pair is completely transferred, leading to the development of full positive and negative charges. But in inductive effect, the electron pair is only slightly displaced from its position so that only partial positive and negative charge appears. Fourth, it leads to delocalization of electrons. No delocalization of electron takes place in inductive effect. In resonance effect, it is transmitted over large distance without undergoing any change in intensity. But in inductive effect, it decreases sharply with the increase in distances and operates only over short distances. Electromeric effect. Electromeric effect is a temporary phenomena which operates during some reactions involving molecules containing double or triple bonds. It consists of an instantaneous and complete transfer of a shared pair of electrons of the multiple bond to one of the bonded atom due to the requirements of some attacking reagent. Electromeric effect is usually denoted by E effect, and the transfer of electron taking place is represented by a curved arrow as shown below. Since A loses its share in the electron pair to B, A requires a positive charge and B gets a negative charge. This structure is evidently not so stable as the normal structure and is formed only at the moment of reaction under the requirement of attacking reagent. If the attacking reagent is withdrawn without the reaction being allowed to take place, electron distribution reverts to its normal state. In other words, electromeric effect involves temporary polarization at the seat of multiple bond. An electromeric shift of electron precedes most reactions involving addition to multiple bonds. Let us for instance consider a molecule containing a carbonyl group when a reagent such as cyanide ion attacks the carbonyl group. One of the shared pair of electrons, the pair constituting the pi bond, is transferred to oxygen. As a result, the carbon atom becomes positively charged while oxygen acquires negative charge, and the attacking reagent immediately forms a bond with the positively charged carbon as depicted below. It is quite obvious that the electron pair cannot be transmitted to the carbon atom because oxygen is more electronegative as compared with carbon. Types of electromeric effect. Electromeric effect can also be divided into two types explained below. First is plus E effect. When the pi electrons are transferred to that atom of the multiple bonds which gets bonded to the attacking reagent, electromeric effect is known as plus E effect. For example, above reactions show the plus E effect. Second is minus E effect. When the pi electrons are transferred away from the atom, the multiple bond which gets bonded to the attacking reagent, electromeric effect, is known as minus E effect. The given reactions show the minus E effect. Significance of electromeric effect. Electromeric effect is very helpful in explaining the mechanism of addition reactions of organic compounds containing the multiple bonds, as will be seen at different places in the text. If both the inductive and electromeric effect operate together, they may assist or oppose each other. In case they are opposed to each other, the electromeric effect generally overcomes the inductive effect. Comparison of inductive effect and electromeric effect. First is It is a permanent effect which involves a mere displacement of electron. But in electromagnetic effect, it is a temporary effect which involves the cleavage of a multiple bond and the completely transfer of shared electron pair to one of the atoms. In inductive effect, there is only a distortion in the shape of molecular orbital containing the displaced electrons. The electrons do not leave the molecular orbital. But in electromagnetic effect, the electron pair of the multiple bond leaves its molecular orbital completely and is transferred to one of the atoms. In inductive effect, the only requirement for this effect to operate is the presence of some polar bond in a molecule. It is not necessary for the molecule to contain a multiple bond. In electromagnetic effect, it can be exhibited only by molecules containing at least one multiple bond, which may or may not be polar in nature. In inductive effect, it does not require any outside attacking reagent, but in electromagnetic effect, it can take place only under the influence of an attacking reagent. In inductive effect, it involves a partial separation of charge, but in electromagnetic effect, it involves a complete separation of charge.